All right, so we are starting basically the last unit of the year. So basically we're doing unit 11, and then we'll do 4 days, a week's worth of algebra review. And you might laugh like, why are we doing algebra review at the end of geometry? Here's the reason why. Your brains have to switch back over. It's like you've been mostly geometry with algebra thrown in. I need to start, believe it or not, before the summer starts, so you walk into Algebra 2 and College Algebra not completely in geometry mode anymore. I need you to start being able to do it. And plus, you just need to review the skills. It's been a while since you've done some of the algebra stuff. But today, we're doing the last hurrah in geometry. Now, we're doing what's called the circles unit. I love this unit. However, most of this unit you've never had before, which means you have a lot of theorems and rules to memorize. Are you guys with me on that? So this would be one of those times where you just need to go back, and I would just start listing key concepts or reviewing a little bit every day. Because of this being so brand new, you actually have 2 quizzes in this unit. So it breaks it into a little bit smaller parts before we get to the test. But you need to make sure that you get all of this info down. Are you guys with me on that? All right, so today we're just going to do a few things. We need to do some remember whens. This was actually, I do believe, the definition of a sphere was on your last test. But this one talks about a circle. And it says a circle is a set of points in a plane that are equidistant from a given point called the center. Now remember, a circle is a 2-dimensional figure. A sphere is what type of figure? 3-dimensional. And so that was really the only difference between them. And I also remember some notation with that. Remember, in order to name a circle, you name it by its center point, and you literally draw a circle with the center as the symbol for it. So that'd be like circle C. We also talk a lot about the interior and the exterior of circles. A reason why it's all about location and just so we can identify stuff. So just remember, if you have a circle, this would be your interior, everything else would be on the exterior. On the circle is the circle itself. So interior, exterior, on are going to be the kind of the terminologies that we use. Now, again, we have a lot of terminology, and this terminology is actually the beginning of your calculus life, okay? For a lot of you, you're going to be taking calculus sometime in your future, either high school or college, and some of the terminology is now going to come out into calculus. So we're going to start using some things that are actually expressed and used in future level courses. Actually, all of our area and volume stuff is all calculus based. You'll be using those as well. All right, so some terms. Now we're going to talk about lines that intersect or segments that intersect circles. Okay? Remember, an intersection is just where 2 things meet, right? It's the set of points where 2 things meet. So when we're working with that, the first one is pretty simple, and you guys have used this term before. It is a chord, okay? Now, here's the key thing. A chord has to be a line segment, okay? A chord is a line segment whose endpoints lie on the circle. So it is a line segment whose endpoints lie on a circle. So looking at the diagram to the right, that means you're going to have a segment. AB is going to be a chord. Now, quick question with you on this. What if I have a circle here? Here's my center, and I draw a chord right there. Is that a chord? What else did we always call that? Diameter. A diameter is the longest chord you're going to get. So when I have a chord that goes through the center of a circle, I'm really talking about its diameter. But its definition would be very similar, because isn't the diameter just a line segment who goes through the center, whose endpoints are on the circle? I mean, it's definitely a chord. So really, a diameter is a fancy chord. Are you guys with me on that? All right, and here's the other thing. It has to be a line segment. It cannot be a line. And it has to stop and end on the physical circle. All right, another term that we use is secant. And this is where it's a line. So a secant is a line that intersects a circle at 2 points. So basically, I'm taking a circle and I'm just literally passing through it. And it's the easiest way of thinking about it. Now, here's the other way of thinking about it. Every secant is going to contain a chord. Because look at line L right here, which is going to be your secant, right? If I put endpoints right there, if I took away the arrows, don't I have a chord? So basically, the way that I tell is like, here's your endpoints, and then if you want to secant, you just keep going, right? So think about that. So A secant can contain a chord. A chord's in a secant. But a secant keeps on going. So it is going to be a line. So that would be line L in this one. Now, I'll just pause in a moment once we get done with all of our terms, and I'll show you where secants and tangents are actually used in calculus. But our next one is a tangent line. Now, this is not, okay, let's do it. We're not talking about SOHCAHTOA, okay? This is another idea. A tangent, in this case, is a line in the same plane as the circle that intersects the circle at exactly one point. So basically, it looks like it's touching it and then it keeps going away from the circle. It's kind of like the story, okay? When you're talking to someone and they start telling you a story and then they go, oh yeah, that reminds me of something, and they go off on a tangent, they go away from that story, right? And they keep going. That's the same type of idea with a circle. Notice right here at line M, I touch it and then I go what? I go away from it. But it always looks like the line is either resting on the circle or the circle is resting on the line. And so the tangent line, in this case, would be line M. Now, of course, we have a special name for the point where a tangent line and a circle intersects. That's called the point of tangency. Now, let me explain to you a little bit where this terminology is now going to be used in your future. A lot of times when you're working in calculus, you will have weird shaped curves. Your goal is to solve for the area a lot of times underneath the curve. Now there's fancy ways of doing this, so just understand. But the way they do that is they work with the tangent lines and secant lines. And a lot of times what they'll do is they'll divide it into smaller parts. So then they will take and we'll draw a secant line. Well, what is a secant line? It's going to intersect it in how many spots? 2. Do you see how I just made a tangent right here then? And then I could do a secant line right here going to 2 spots. And notice it just intersects it at 2 spots. And I can do that all the way around your curve. So when they use secant lines and they're estimating area underneath the curve in calculus, you know you're going to intersect it in 2 spots. And you're going to cut off a little bit as you go. Make a little bit of sense? Now, so that's working with secant lines. But what if I had another type curve? Let's say I had something pretty simple like this. And I'm working with calculus, and then I'm talking about the tangent line. Well, this is talking about derivatives and using them. So they actually talk about the slopes of tangent lines in calculus. So a lot of times with the tangent line, they'll sit there and you'll draw it, and it intersects it at 1 spot. You see how that little line just barely touches it? And then they will just sit there and draw another one, and it barely touches it. This one would barely touch it. So here's the thing. At every point of tangency there, I have a different line with a different slope, right? You will use the idea of slopes of those tangent lines in calculus. So the idea of tangent and secant, even though we're talking about circles, which is a lot easier to see secant and tangent with, that's a concept that gets moved to calculus. So here's why we're learning it. So yeah, 2 years from now, you're going to care. Not this very moment, but about 2 years. Does that make sense? So there's a why we're going to do it. But now, right now, we just got to be able to identify it real quickly. All right, so let's have a little bit of fun. All right, it says identify each line or segment that intersects circle L. So we want to know every type of thing that we can do. So let's just start with what we're doing. Let's go down. Let's do the first one. How about a chord? Can anyone give me a chord, please? Come on, shout them out. Chord has to be a line segment. What are my line segments that are chords? All right, say KM. I heard another one. Someone said J what? JM. Excellent. Could I be even more specific and use the word diameter here? Could I say diameter segment KM? Notice segment KM is in both locations, right? Because a diameter is a chord. So that's why. Yes, but isn't also segment JM part of that, right? Remember, that's the difference between a secant and a chord. You're right, but JM will be a line. We're going to keep using that. So then we're going to go to the next thing. How about a secant? Which would be line what? Basically, you take a chord and keep what doing to it? Keep extending it. So then you get line JM. Notice notation is everything on this. A line segment and a line, 2 different things. Line segment JM, a chord. line, JM, we got a secant then. So you gotta be very careful with that. Do we have any other secants on there? No other ones that were drawn anyway for us. Exactly. All right, so what's gonna be our tangent, guys? Yeah, so that's gonna be line M. All right, now, we're not done with the line or segments here with this one. There's still other things that are on there that still intersect the circle. Anything else that we know that we've been using quite a bit already that intersects a circle? How about the radius, right? So don't we have radii for this circle? Don't we have segment KL, because K is a point on the circle, that's one radius. Don't we have segment, isn't that JL is the other one, and segment LM? Are those true, guys? Now, the one thing that's not a line or a segment, so this is not required on here, what's the only thing we haven't talked about yet? Point what? Point H. What's point H called? Yeah, over here, we just know that point H is the point of tangency, and we're going to be using that more tomorrow in the future days, so just make sure you know that. But those are all the different things you can get from that circle alone. You have like 1 or 2 problems like that on your homework where you just have to identify stuff. Notation matters. Did everyone hear me on that? Notation does matter. All right, so some review. I didn't want to put everything on here that we've had before, so quick review with this one. Congruent circles are circles that have the same radii length, so they have the same radii. Also, concentric circles, remember we talked about the target sign and whatever, they have a shared center. So again, we're just reviewing some terminology. But now we have a new term that we had to have, and it says the following. 2 coplanar circles that intersect at exactly 1 point are called tangent circles. And they're described 2 ways. They're described internally tangent and externally tangent circles. Notice the internally tangent circles. Do they share a center? No, they don't share a center, but they share that 1 point. So think about it. Could they share a tangent line? Totally. How about our other ones, our externally tangent circles? You can see how one's not inside the other, but they're still intersecting at 1 point. Could they share a 1 line of tangency also? So a lot of those things, pretty simple and straightforward stuff that you have to know. All right, now let's actually go back to, get this, Unit 3. Are you guys so excited? We're going to go back to equations of lines today. Easy ones though, only vertical and horizontal lines, so we're fine. All right, so it's not hard stuff. All right. So a couple problems like this on your homework, very straightforward type things. It says find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. By the way, are these circles externally or internally tangent? Externally tangent, great. So let's find the length of each radius. So what is the radius of circle S? What is its length? Don't overcomplicate this, you should eyeball it. Should be like 3/2 or 1.5, right? So 3/2 units or 1.5, I'm good with. Because its whole diameter is 3, so 3/2. I know, real exciting. Rough math. And then we have our radius for our other circle. So radius of circle R. Guys, what's the radius of circle R? What's its length? Yep, it's going to be 2 units. All right, now we're supposed to identify the point of tangency. If I'm talking about a point, isn't that an ordered pair, my friends? So what ordered pair tells me my point of tangency here? What is that ordered pair? It's a -2, 0. All right, excellent. And then it says I'm supposed to write the equation of the line. So basically, isn't this the line I'm looking for? What type of line is that? Horizontal or vertical? Horizontal. What's the slope of a horizontal line? So isn't my slope 0 on this? I have a slope of 0. I have an ordered pair. Can I write the equation of a line? Yeah. So the equation of, let's see, I'm going to try to abbreviate this, of tangent, not abbreviating well at all. What would be the equation of this? Can anyone do the shortcut method of doing this? Does anyone remember? If you have a horizontal line, what's the only number you really have to worry about? It's your y-intercept. What is it going to be? There's your equation of your line, y equals 0. Or, here's where most of you should go. Okay, I'm telling you this right now. This is where most of you should do. Most of you need to use point slope form and get it right. Okay, most of you need to go, okay, I know y minus y1 equals m times x minus x1. Can I put in what I know? I have y minus 0 equals, what's my slope value? Times the quantity x minus, or excuse me, not x minus, x what? X plus 2. I would take either one of those. Now on your homework, you might actually have a vertical line. You guys remember how to do vertical lines? There's only one way. Yeah, it's your x-intercept. So it's just x equals whatever your x-intercept is. So your x value. So don't forget, they're meant to be that easy of lines that we're doing today. They're not meant to be overly complicated on there. All right, again, I'm giving you one example. You have like 2 or 3 on your homework. Don't be afraid to look at the examples in the book. They actually were decent on this, so I can't yell at them on it. All right, some other terms that we're going to talk about. Common tangents, okay? A common tangent is a tangent that's in common with 2 circles. And there's 2 different types, and this kind of makes sense again. We talk about them being external tangents, or we talking about being internal tangents. So external, and here's our, actually I want to highlight that first. Now, what are so special about these? You'll see actually in a little bit, but I want to talk to you about this. Notice with this, we're going to use a couple ideas anytime that you have common tangents. A couple of things that you're going to do is you're always going to be able to draw in a radius, no matter what. Also, realize that top line and the bottom one, don't they look almost exactly the same? Different slope, but are they like almost touching the same way on each circle and everything, right? So those are huge. We're going to use these. The ones over here on the right, the ones that are called the common internal tangents, you don't see them as often, but when you do, you're supposed to remember how to work with similar triangles. Let me show you how to see this real quick. A lot of times what they'll do with these, no matter what, is they will always connect the 2 centers. Then, using the theorem that we have down below, and I'll talk about to you in a little bit, I draw the radius into a point of tangency. And notice where I'm drawing them. And I'm drawing a right angle. We'll talk about why in just a moment. But I'm drawing that right angle. I want you to look at those 2 triangles for me. What's so special about the relationship? Are they the same size? They're not, right? Are the circles the same size? No, they're not the same size. But what's so special about those 2 triangles? They're similar. Because do I still have these lovely thing called vertical angles? And by similarity, those 2 triangles are similar. They expect you to know that after you haven't seen it for forever. So just know, anytime you see the common internal tangent ones, by the way, which have been known to show up on homework problems this week, you are going to realize that those are similar triangles, and you're going to have to, oh yes, here it comes, matchy people, matchy. Doesn't go away. I would advise, actually, for a lot of you, start reviewing your quadrilaterals and similarity units. It's been that long. It's been a long time. All right, let's talk about our 2 theorems that I actually drew one of them up above with the common internal tangents. It's the following. If a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. Basically, that means if I draw a tangent line, look up here above, guys, I have every right to draw in that right angle that you just saw. Think about this top one. I can draw in the radius to the point of tangency, and oh look, I have right angles. It's amazing. Could I make quadrilaterals show up? Ooh, you know, all this excitement and everything. So you're going to be using that concept over and over again. So the moment you see a line that's tangent, you can automatically draw in a radius and get a right angle every single time. In fact, that's probably the number one thing I'm going to tell you is, like, make sure you mark up the right angles with this. And in fact, this is what's in my notes. Mark your, I bet you guys aren't surprised by this comment, diagrams, right? Mark them up if you see this. Now, the next one is literally just the converse. As I move it as I'm writing, that was kind of funky. All right, if a line is perpendicular to the radius of a circle at a point on the circle, then the line is tangent to the circle. So I use it both ways. And guys, right angles, do you think right triangles and quadrilaterals and all that fun stuff are going to show up? Yep. And so this is one of the biggest concepts that we're going to use today. Are you guys ready to crank this out? All right, let's have a little bit of fun. Let's do the very first one. All right, early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. What was the distance from the spacecraft to the Earth's horizon, rounded to the nearest mile? So basically, I'm looking for the length of segment EH. Now, I'm given the following. The altitude above the Earth is 120 miles. So guys, only from here to here, that's 120 miles. Now, is this drawn to scale? You bet it isn't, okay? But don't get me going. I'm going to talk about my new favorite movie, you know, Hidden Figures, pretty soon, if we keep using this example. If you haven't seen it, you need to watch it, okay? I'm just telling you. All right, now, here's the thing. Notice, what do they draw in? What do they have there? Do I have my radius to a point of tangency? Notice they don't have the whole tangent line drawn, but could I just extend this and make it a tangent line? Yeah, you could totally do that, but you don't need to, because I have this thing called a right triangle I now can use. Now, the whole thing is I really need to know the distance or the length of segment EC. Guys, what's the real length of segment EC? Yeah, it's 4,120, because aren't the radii of my circle congruent to each other? Right triangle, I know two sides. Oh, wait, how do I solve for the third side? Pythagorean theorem, right? Leg squared plus leg squared equals hypotenuse squared. So I got x squared plus 4,000 squared equals 4,120 squared. This is when your calculator should be out by now. So I'm solving for x squared. I get 4,120 squared. Notice I know we're going to use calculators. I'm not simplifying that more on my own. All right? So I get x squared. Now, for those of you, most of you have been punching into your calculator by now, it's really 974,000 is what your x squared is. Almost a million. What do I need to do both sides? Take a square root of that, and it said to the nearest mile. Remember, I put plus or minus there, but we know it's going to be a positive distance. Someone get that to me to the nearest mile on their calculator. What did you get? All right, so 987 miles. Wow. That's 987 miles. This is so not drawn to scale. So not a Hidden Figures thing. They would have already known it by now. It's taking them seconds. Us, a longer time. All right, anyway. Guys, what do you think? It's really not bad if you know rules, right? We're just pulling everything we've been learning and putting it all together now. Here's some other ones. Let's assume that the line appears to be tangent or tangent. All right, I love this. So assume that the lines appear to be tangent or tangent. Point C is the center of each circle. Find the value of x. Talk to me. When you look at that diagram, what do you guys see? Does anyone see a radius? Does anyone see a point of tangency? Does anyone see a portion of a tangent line? If I have a radius to a point of tangency, what should you draw in? You should draw in with glowing colors, my friends, a right angle. Because the moment you do that, can you quickly now solve for your angle measurement? Yeah, guys, how are you going to solve for x? What are you going to do? You said x is going to be 90 minus 58. Did you guys get 32 degrees? When I was doing this yesterday and I was half asleep, I was 42. So today I was watching for my air to make sure I didn't do it. All right, so it'd be 32 degrees. Now, if you forgot that the acute angles of a right triangle are complementary, could you have also done this? 180 minus 90 plus 58. Would I still end up getting 32 degrees? Yeah, either one of those are fine. Mark up your what? People, if you don't mark up your diagrams, it's going to be very hard on this unit. Okay, we're going to mark things up. All right, look at the next one. That one looks kind of fun. Does anyone see like two portions of two tangents that intersect outside the circle? I see two radii. I also see an angle that's 130 degrees and an angle that's x. What do I need to mark in my diagram? I need to mark how many? What else do you know? How can I solve for x? There's a couple different ways. JD, what would you? You totally can do that, and I'm going to talk about that second. So we'll go there in a moment. Like he said, we can split it and make two triangles. Wonderful. How about if we back up and say that's a quadrilateral? Can I use the fact I know the measures of the angles of a quadrilateral? Think about this for a moment. What are the sum of the interior angles of a quad? I'm using this formula, right? We know that's going to be 360. Do I know 3 out of the 4? If I know 3 out of the 4, can I go 360 minus the sum of the other 3? And I think you get, I think it's 50 degrees. Correct? Now, JD told me another way of doing this, and actually I agree with him. There is another way. Could I draw this in? If I do, what's so special about those two triangles? They end up being congruent by hypotenuse leg, right? Because the hypotenuse are going to be congruent and the legs are going to be congruent. So by hypotenuse leg, they're congruent, which the cool part is that means this angle is being bisected. And what's so special about this angle? It's going to be bisected. So could I go and use the fact that this angle is going to be 65 degrees, and I can go, okay, and I'm going to call this y for now. Y is going to be 90 minus 65, which is going to give you what, 25? But how do I solve for x? I got to do what to it? Multiply by 2. Did I still get 50 degrees? I don't really care which way you did it, as long as you showed me work, right? As long as I know the process that you did. Either one of those are valid ways of doing it. I like the first one because I don't have to worry about bisecting and doubling something. But you have to be really good at recognizing your right angles, and you have to recognize it's also quadrilateral. Does that make sense, guys? So JD, that's how you're going to do it, weren't you? A lot of people naturally do it that way, which is a good way of doing it. All right, let's look at another one. It says, in each diagram, ray AB is tangent to circle C at point B. Find the value of x. What's the number one thing you should do? Mark what? Mark your right angle, correct? The moment you do that, what type of triangles do you have? What type of triangles? Right triangles. How are you going to solve for the missing parts? Your only option is Pythagorean theorem. Do I know anything about angles on this one, guys, besides the right angle? No. But here's the thing you need to be very careful. Guys, what's the length of segment AC? Is it 2x or x plus 2? Which one is it? Yeah, it's x plus 2. So when I do this, I have leg squared plus leg squared equals x plus 2 squared. All right, guys, remember, poor algebra really gets you on this one. You could get x squared plus 64 equals, what's the quantity x plus 2 squared? It's going to be x squared plus 4x plus 4. What did I do to get that? Let's do sidebar over here. What's x plus 2 squared? Isn't that the same thing as x plus 2 times x plus 2? What do we have to do? FOIL. X times x is x squared. X times 2 is 2x. Inside 2x, last 4. Oh, look, x squared plus 4x plus 4. Remember at the beginning of the year, I've done this several times to you throughout the year, making you FOIL those. So this you have to remember over here, because once you do that, life gets really good. Because it looks like I have to factor, doesn't it? But look what happens when you subtract x squared from both sides. The sweetness in itself, it goes away. Once in a while, it's beautiful. And then you subtract 4 from both sides. And you get 6 equals 4x. Guys, what's x going to equal? Now I want to show you something. If this is 15, what's this one going to be? 8 15, 17 triple. Not drawn to scale, but sure makes sense number-wise, doesn't it? All right, what do you guys think? Easy or hard? Fairly okay? All right, let me put this way. Doable, livable, okay. All right. So with this one, let's look at the next one. Are we going to draw in our right angle, our radius to the point of tangency again? All right, so we have our right angle. Note it, be careful. The biggest thing is make sure you put your hypotenuse in the right spot. Do you guys agree with me? My hypotenuse is 10. I have a leg that's x. What's my other leg length? It's going to be 3. Because what do we know about the radii of a circle? They're always congruent, correct? So if I know one's 3, don't I know the other's 3? So then we just use our math again. We get 3 squared, so leg squared plus leg squared, so 3 squared plus x squared equals hypotenuse squared. So I get 9 plus x squared equals 100. X squared is equal to 91. Gotta love our math. Okay, plus or minus, x is going to be the square root of 91. That's it. What do you guys think? This isn't bad, is it? Not really. All right, let's keep going because there's so much more fun stuff to do with this. Yeah, we do. We got to speed up. All right, last but not least, on this one, can I put in my right angle? Do I know the radii are congruent? Now I want you guys to hesitate for a moment. You have a leg that is 9, a leg that is 12. What is your hypotenuse? What is your hypotenuse? 15. Do you need to waste your time than doing anything more than this? All right. Now, there is an or to this. If you forgot that, you, my friends, would need to use the fact of factoring, and it works out perfectly with factoring. But you would have to factor to solve. Here's the thing. It's filled in notes. Are you guys with me on that? So if you want to go and remember how to factor, it's there. So if you get stumped, did everyone hear me? If you get stumped on this, can you go back into your notes and see an example of how to factor it? Great. If not, just know your triples. They save so much time. All right, now these two. Love these problems. People get it wrong every year. Here's what I need. Do we have external tangents right now? So my two examples of two external tangents. The key thing is making sure you draw in your diagram carefully. So there's two right angles. I'm going to draw them in for both diagrams before I forget. I'm looking for two different things. I'm looking on the first one, I'm looking for the distance between the centers of the circle. It's a very common one that we use. If you do this, this is how you do it. Are you guys with me? If you don't do it this way, people mess up. So pay attention. Go to the center of your smaller circle and draw a line segment parallel to your tangent. And what I want you to do is I want you to basically form a rectangle. Now this is not going to be drawn to scale. Did everyone hear me on this? There's no way this is going to be drawn to scale. But the moment that I do this, do you agree with me? If I drew that, that's parallel. Did I just create a rectangle? I just created a rectangle. And so I know the opposite sides. Let's see if I can turn that to red. It might be a little bit easier to read. I know my opposite sides are going to be congruent. Oh, wait, that means from here to here is 9. What's left for down here? 3. Oh, look, I have this weird, very narrow shaped right triangle. I have a leg that is 3, a leg that is 25. Can I now solve for the hypotenuse? Yeah. So when I do that, I get 3 squared plus 25 squared is equal to x squared. So I get, nope. Where's the right angle? Remember, a hypotenuse has to be opposite. This has to be the hypotenuse because it's opposite the right angle. That's the hardest thing to recognize. And that's the most common error that you guys, I'm just so glad you brought that up because that's a very common error. People put the long leg and the hypotenuse since they're so similar in length, it's very easy to confuse the two. All right, let's do the math real quick. So I got 9 plus, guys, what's 25 squared? Is that 625? Let's hope my math is on. All right, so 625 equals x squared. So that's 634. All right, now people who are very much better probably at radicals than me on this, I didn't find any last night when I was making the answer key. So we're just gonna leave it like this, the square root of 634. It doesn't mean there is not probably a perfect square radical. I just didn't find it off the top of my head right away. And probably, you know, half the time the book would say round to the nearest hundredth anyway, right? So just make sure that you have that down. Now, the same type of process I'm gonna use. But here's the key thing you need to remember. You start at the center of the smallest circle and you draw it parallel to your tangent again. So that means these are gonna be congruent, those are gonna be right angles. Now, here's where you've got to be careful. Again, I'm using opposite sides, so that segment would be x. From here to here, that's 2, which leaves this one to be what? 1, right? Guys, what your Pythagorean theorem, what is it gonna be this time? Think where your hypotenuse is. What do you have?
The first problem is that, wait, is x the hypotenuse? Oh, x is the hypotenuse.
Yep. It's hard to see because of the small right angle there, right there, isn't it? No, that's a good thing to ask. So same type of a scenario here. Isn't this still my hypotenuse? Yeah. So if that's the case, I get 1 squared plus x squared equals 7 squared. So I get 1 plus x squared equals 49. So I get x squared is equal to 40 what? 48. Now guys, when we simplify this, we've got to simplify it to its simplest radical form. What is the largest perfect square number that comes out of 48? 16. What's the square root of 16? So it'd be 4 root 3. Guys, read directions carefully on this chapter. You'll be going from exact form to rounded a lot. So just read between the two. All right, this should be your hardest problems. I'm pretty positive they will be. All right, last but not least, our last theorem, which I think is actually common sense because we've already used it. I just didn't tell you guys that we were using it. It's called, I call it the two changes theorem. This is not a name that they have. This is just a common theorem, but to me it makes sense because there's two what? Tangent segments that are right there. Isn't that earth-shattering? I know, common sense. But I named it. It's not a name in the book. It says the following. If two segments are tangent to a circle from the same external point, then the segments are congruent. Now notice how they do this. They talk about the segments being tangent. So is such a thing as tangent segments? Yes. So we're going to be able to use that. Now, guys, here's the y, okay? The y is exactly the same thing that we used way up here on part B. Because look what happens when we draw things well. If I draw these in, can I draw the radius in? I'm going to do a different color here. Can I draw the radius into the point of tangency and form a right angle? Can I draw another one and form the right angle? And everyone goes, yeah, that makes sense. We can do that. Can I draw a segment PA in because any 2 points determine a line? The moment I do that, do I have congruent radii, which are going to be congruent legs? And do I have the hypotenuse of each one of those triangles? Are they congruent to each other? Guys, if I have a leg and a hypotenuse, how are those two triangles are congruent? Yeah, so the triangles are congruent by hypotenuse leg congruence. If triangles are congruent, what do I know about corresponding parts? Oh, guys, what does CPCTC stand for again? That's correct. Corresponding parts congruent, triangles congruent. So the triangles are congruent by that, and then we know that segment AB is congruent to segment AC by CPCTC. So basically, those good old-fashioned congruent triangles that we try to forget that exist still work. And that's why we know those two segments are congruent to each other. Isn't that kind of cool? So it's basic. It's one of the easier proofs to prove. So now apply it. The moment you see two tangent segments are from the same external point, you automatically know they're congruent to each other. So here's my thing. Mark it so. Because it says find the length of segment HG. Well, can I set them equal to each other? And the answer is yes. So let's do it real quick. So I get 5a minus 32 is equal to 4 plus 2a. When I am solving this, I end up getting 3a is equal to 36. And I get the fact that a is equal to 12. Plug and chug. You should get the fact it's 28. All right, we're going to skip the next example so I can do at least one example at the bottom here. Are you guys ready? All right. Now, remember what circumscribes means, right? It goes on the outside. Inscribed goes where? Inside. Now it says in each diagram, a polygon circumscribes a circle. Find the perimeter of each polygon. Notice a problem here. I am missing this line segment, but we can use our last theorem here. Because if I talk about those tangent segments, do you guys agree with me that these two segments are congruent to each other? Do you also agree with me? Let's see if I can do this quickly. The bell might ring, guys. I need you to stay with me while we're doing this. These two segments are the same? And would you agree that these two segments would be the same length? Is that all true? Using our last theorem. All right, now let's mark things up. If this segment is 6 from here to here, what's the distance from here to here going to be? What's left from here to here? Which means that one's 3. Well, if that's 3, what's the length of this segment? Doesn't that make that one 5? Because basically, if I've used up a portion of it, do I have what's left over? So then what's the length of this whole side? What's 6 plus 5? 11. Oh, look, now I have perimeter. Perimeter is 9 plus 8 plus 11. Did you guys get 28 inches? You just got to keep doing that all the way around. I think we got an example of every single type of problem in. Are you guys good? All right. Filled in notes have every example filled in for you guys. Good job, guys.